to this first lecture on signals and systems. Alright. Let me begin by wishing you all a happy new year, and also trying to place in perspective the course that we are going to teach this semester. Well, I assume that this perhaps is not the first course in electrical engineering that you are studying, and this might not in the true sense be the first exposure to signals or to systems, although it would be the first formal exposition. You have already looked at signals and at systems from a different perspective. You've had a whole course on networks, probably. In some cases, the student could have had a course on electrical circuits. So, even if not directly, indirectly, you do know what a system is, and you also know what a signal is. But at this point in time, perhaps our vision, our perspective on both of them is a little restricted. We understand the notion of a system operationally. We understand the notion of a signal operationally. That means in a context. I can use the idea of a voltage signal or a voltage waveform. We are probably not so accustomed to calling it a signal, we've been calling it a waveform, right? Essentially a matter of terminology, but there is a slight difference. We'll bring it out later. And we've been accustomed to dealing with voltage waveforms, current waveforms, perhaps power signals, right? And what we've been doing is not really to look at the signal as a signal per se, but as some other entity that serves some other purpose, right? Or for that matter, even the system. We have not really looked at the system as a system. We've looked at it as an entity which serves some other purpose. To take an example, if we look at the capacitor, which we've been dealing with extensively, we think of it as an element which differentiates the voltage, right? But we don't really look at the capacitor as a system in its own right so far, right? The same thing holds for other systems that we have encountered. The examples that I gave so far were essentially electrical systems and electrical signals. But we could also take mechanical signals. For example, one might have been accustomed to dealing with displacement patterns, velocity patterns, right? Force patterns. Now, there again, we have studied these in a context. So we have agreed that, a force as a function of time produces a certain effect in terms of velocity or acceleration or displacement as a function of time, right? To take another example, we might have looked at thermal systems when we studied heat, right? So we also looked at the effect of a temperature difference. So there again, we didn't worry about the temperature difference from its essential signal characteristic. We said, well, this temperature difference pattern would result in this heat flow pattern. In all these examples, we've been looking indirectly at signals and also actually at systems. But we have not bothered to extract from all these situations the common element or the common features, the common abstractions that make all these situations amenable to one kind of analysis. So what are we trying to do? Extract from a wide diversity of situations, whether mechanical, electrical, hydraulic, thermal. It's irrelevant. Which situation at this moment is going to become irrelevant. That's exactly the opposite of what it's been so far. So far the situation was relevant, the abstraction was irrelevant. Now the situation is not relevant, it's the abstraction that is relevant. You'll understand what I mean as we proceed. Well, let's proceed by taking the example of an electrical system, since that's what most of the audience might be familiar with. Let's assume that you have voltage waveform across a capacitor, and you look at the current waveform in the capacitor. What is the relationship? We know that the current waveform in the capacitor is proportional to the derivative of the voltage waveform. Now, in this example, we subsumed all that we want to do in our elementary understanding of signals and systems. There are two signals here. There is a voltage signal and there is a current signal. One could also think of a cause-effect relationship here, though it's not rigid. For example, if I have a voltage source applied to the capacitor, and if I place an ammeter in the circuit, assuming the ammeter is ideal and that it can respond as fast as the current varies, right? It can respond precisely the current waveform, right? We would think of the current here as an output then. So if I have a voltage source across a capacitor driving the capacitor, there is a difference in status between the voltage and current, right? The voltage acts as an input and the current acts as an output. And both of them are signals in the sense that they are functions of time. Actually, there's nothing more to a signal at first glance. It's a function of an independent variable, right? And there is the system, the capacitor, right? What does the system do? It responds to the input signal in a certain way to produce the output signal. So if I have a voltage waveform as an input, then the current waveform is the output. There are two signals and one system, the capacitor. The capacitor is a system which has its own description, just as each of the signals has its own description in time. So for example, if it's a direct voltage or DC, how would you plot it? As a function of time, it would just be a constant, right? If it's a sinusoidal voltage, then one could plot, I don't think I need to actually illustrate to you what sine waves or DC look like, but one can visualize that one can plot the waveform as a function of time, right? And that's a description of the signal. Signal, description of the signal, right? What is the description of the signal that we are talking about here? What is the most general description? A tabulation of the values of the signal as a function of time. That's the most general description, right? Where is the system? The capacitor is a system. What is the description of the system? Well, in this case, there's a very simple description. The output current, in this case, is proportional to the derivative of the input voltage. System description. System, capacitor, system description. Output is proportional to the derivative of the input. Alright? Signals are easier to understand. Right? Systems are a little more tricky. In fact, systems are one step higher in the hierarchy. Alright? Let's take another example of a system to illustrate. Intentionally not electrical. Let's take a mechanical system. Let's take a mass, just a mass. Right? See, one way to think of Newton's laws is to think of it as a relation between force and acceleration. Another way to think of it is to think of it as a description of a mass. So you could say, well, a description of a mass element, is that it relates the force and the consequent acceleration through a proportionality constant. That's the mass. Right? I'm intentionally putting before you a slightly different perspective, which is useful to us in this course. So here I treat the mass as an entity, as a system in its own right. Right? And I say, well, based on Newton's laws, the force is proportional to the acceleration in the case of a mass, and therefore I could think, well, there are different ways in which I could look at signals here. I could look at the force signal, so I could have a force as a function of time, right? And therefore I would have an acceleration as a function of time. And in this case, normally one would assume that the force is the input. It's unlikely that it's the other way, right? The force is the input and the acceleration is the output. Or it could also be that the velocity is the output. In which case, what is the relation? The relation is that the force is proportional to the derivative of the velocity. Is that right? Okay. Now, this brings into picture what we call an analogous system. So for a moment, suppose we visualize the velocity to be analogous to a voltage, right? And the force therefore to be analogous to a current. What is the situation? The force is proportional to the derivative of the velocity. Alright? In the language of analogies, the current is proportional to the derivative of the voltage. So there is a common element here, right? In fact, here one might go to the extent of saying the mass in this sense behaves like a capacitance in an electrical circuit. Is that right? Why is this important to us? For two reasons. One is, of course, it's interesting to draw parallels between different disciplines and to come to some similar methodologies of analysis. The other, an equally important reason, is to bring out abstractions from the situation that captures both of them, which makes them independent of the situation. So now, being an electrical engineer, I am constrained to think in terms of capacitors, inductors and resistors. A mechanical engineer might be more inclined to think of springs, dashpots or resistance elements and masses. But we'd like to get around these limitations in perception. Right? That's the aim of this course. So we'd like to extract from both these situations the common abstraction. There are two signals involved. There is a relationship between the signals, and what we mean by an analogous system is that the system behavior is the same. So from the point of view of this course, the two systems are identical. It doesn't matter that one of them is a mechanical system, the other is an electrical system. We don't look at those differences in our discussion in this course. That is the philosophy. That is an equally important point, and something that helps us then to abstract to many other situations. Today it's mechanical. Tomorrow there could be a similar hydraulic system. Right? But once we have the tools for analyzing, or once we have the methodology for analyzing such a situation, we can apply it to any circumstance and come out with meaningful results. Right? Now, I think we should begin by formalizing our idea of signals and systems. As I said, we've already been exposed to both of them indirectly. Now we shall expose ourselves to them directly. Now, we'll agree that at least for the initial part of our discussion of signals and systems, we'll talk about an independent variable, right? And most of the time, we shall assume that the independent variable is time, right? So, at least at first, for first analysis, for initial analysis, or for understanding, right? Independent variable is time. We shall use t to denote time. So it's very simple. Although we might add a little bit to this definition later, at the present moment, we shall be content in bringing out a very simple definition of a signal. A signal is a dependent variable of time, or of the independent variable. Signal, a dependent variable. There is no end to examples, right? voltage, current, right, power, force, velocity, acceleration, all as a function of time. Now, we must caution at this stage that this is not the only kind of signal and this is not the only possible independent variable. The independent variable could also be space, for example. So you could have a force as a function of space. And you have been exposed, I think, to the cantilever arrangement, yeah, in your courses on physics. You might have been, is that right? You've been exposed to, yes, cantilever behavior, yeah? Or, suspended rod behavior, yes? So you often have force as a function of space. And there, you could also, the mass distribution could be a function of space and so on. Right? So there is an equally good and equally useful set of signals which have space as the independent variable. And it could also, you see, here again, we have to be a little more general now. You see, time is inherently one-dimensional. That means there's just one independent variable. But now we must be more general and say there could be more than one independent variable. Particularly when we talk about space. So an image, for example, is also an example of a signal. But it has two independent variables. So, we must, let's say generalization. Multiple independent variables. Yeah, so for example, two-dimensional space. And then in that case, the signal is of course still a dependent variable. But what is the example then? An image. Picture. Yeah? You could have hybrid independent variables. Yeah? So one can have multiple independent variables and hybrid. And what could be an example? Two-dimensional space and time. The signal is still a dependent variable. And what is the example? What we are doing right now? What is the example? A video. Yeah. So you can be loud and answer as you used to do in the class, right? I mean, and you'll also be captured on camera, so it's a great honor. Yeah? So you must answer loudly. There's nothing to be ashamed of if you have either the right or the wrong answer. In fact, it's an honor to be captured with the wrong answer because you will help somebody else correct his notions. Right? So it's a good idea to make mistakes at times. Right? Now, it's clear to us that there is a wide class of independent variables. There's a wide class of hybrid independent variables also. This is one example. There could be others, right? My suggestion to you is, now, when you go out and when you look at other subjects or when you look at other engineering situations, make it a point to identify signals in the situation. It helps. If you really wish to grasp the fundamentals of this course properly, consciously or maybe even subconsciously try and make it a habit to identify signals in the situation that you're dealing with and try and put them in this framework. Yeah? That's what we want to talk about as far as signals go at the moment. What about systems? Well, systems are, as I said, one step higher in the hierarchy. That means they are going to use signals, right? What is a system? In very brief terms, a system is a mapping from an input signal to an output signal. All right? So what is it that describes a system completely? A tabula, yes, yeah? Yeah, anyone? Yes?
Then put an output of there.
Yeah, loudly, yes, Sharangi, loudly.
The input and output that is concerned to a system and to a signal that corresponds to a system. Signals of passing through a system that corresponds to that really specifies the system.
So Abhishek says it's the inputs and outputs that pass through a system. Well, there is a little but very important part that's left out there. Yes, Uday? Initial conditions. Uday says initial conditions. Alright, I think what we'll do is we'll leave it in suspense at this point and take it up tomorrow. Yeah? So we'll conclude the lecture here and we'll take it up from this point of discussion tomorrow.